Laparoscopic surgery forces surgeons to operate through a tiny keyhole. They lose the tactile feedback of open surgery, relying entirely on a flat, two-dimensional video feed to navigate complex anatomy. The primary objective of surgical data science is to take that raw, unstructured visual stream and translate those pixels into an objective, real-time map of the surgical environment. This schematic maps the core pipeline to build these tools. It begins by extracting frames from the raw surgical video. Those frames must then be manually annotated by surgeons, creating the ground truth data necessary to train the algorithms. To achieve clinical utility in the operating room, an AI system must synthesize two distinct models. It has to accurately map the spatial geometry of individual frames, and it must track multi-hour surgical processes temporally. Relying solely on human visual interpretation leaves room for subjective error. Objective algorithmic measurement is the necessary next step to reduce that variability and ensure consistent patient safety. This set of images illustrates surgical scene understanding, the foundational capability to identify tools, tissues, and structures within a single frame. Convolutional neural networks calculate precise bounding boxes and labels around metallic instruments, allowing for real-time detection. But drawing a box around a grasper requires less precision than mapping the exact edge of an organ. For precise pixel-level boundary delineation of complex anatomical structures, engineers rely on symmetric encoder-decoder architectures, particularly U-Net variants. In a standard deep neural network, high-resolution spatial details are often lost during compression. U-Net bypasses this limitation using skip connections, allowing raw image data to route around the deep bottleneck and feed directly into the expansive decoding layers. Recently, researchers have begun replacing these convolutional networks with vision transformers and detection transformer models, or DTR. Instead of evaluating localized patches of pixels, transformers use a global self-attention mechanism to analyze the entire frame simultaneously. Because of this global view, DTR utilizes set prediction mechanisms. The model maintains a robust lock on surgical tools, even when they are heavily occluded by surrounding tissue, smoke, or fluid. Transformers offer superior spatial mapping, but their massive computational weight presents a severe physical constraint. Intraoperative tools require a strict latency budget of 50 to 100 milliseconds. If the model is too heavy, it cannot process the video stream fast enough to be useful. Identifying a scalpel or a gallbladder in an isolated frame is a spatial achievement, but it does not tell the system what phase of the surgery is actually occurring. To establish context, the system acquires surgical process understanding. It must map dependencies across multi-hour procedures to classify whether the surgeon is in a preparation phase, a resection, or a closure. This diagram details the two-stage pipeline for temporal recognition, specifically the techno model. First, a convolutional backbone takes the incoming video sequence and compresses frames into dense spatial feature vectors. These vectors pass into temporal modules, which process them sequentially. By stacking dilated convolutions, these networks evaluate long historical sequences of the video feed simultaneously, avoiding the vanishing gradient problems that cause older models to forget earlier events in a procedure. Engineers are now pushing this further, deploying models like SurgeFormer that replace temporal convolutions entirely with self-attention mechanisms, mapping procedural context spanning several hours.
Linking spatial targets across time graduates the AI from a passive visual observer to a system capable of anticipating the next required procedural step. Anticipating the next step provides workflow context, but assessing a surgeon's actual proficiency requires combining these into a highly structured relational format. Engineers utilize the action triplet framework for this, codifying every activity into three distinct variables. First, an instrument, then an action, and an anatomical target. Instead of simply tracking a tool's position, the model outputs a structured semantic log of the procedure. For example, grasper retracts gallbladder. Advanced models map interactions through self-attention and cross-attention mechanisms, calculating the relationships between instrument and target to classify actions. The primary hurdle is disentanglement, isolating the tool and tissue from visual noise, like smoke, highlights, or blur. Training algorithms to ignore that noise requires massive amounts of labeled data, and right now, comprehensive triplet annotation is severely limited, bottlenecked to specific datasets like Cholik 50. Achieving this structured relational representation is the mandatory precursor. Without it, mapping the exact interactions between tools and tissues to create automated, objective surgical skill assessment is impossible. Moving these spatial, temporal, and relational architectures out of the lab and into the operating room shifts the objective. The algorithms must now provide high-stakes clinical decision support. A prime application for this is the critical view of safety, or CVS. It is a universal visual heuristic used during laparoscopic cholecystectomy to prevent severe bile duct injuries. To safely proceed, a surgeon must meet 3 strict anatomical criteria: expose the cystic plate, clear the hepatocystic triangle of fat, and isolate 2 visible tubular structures. Automating this validation starts with spatial perception. Models like UNet process the incoming video to generate precise semantic segmentation masks, explicitly defining those required anatomical zones. But colored pixels alone cannot confirm safety. Engineers convert those spatial masks into a semantic graph structure using a graph neural network. Nodes represent the centroid of each structure, and the edges calculate the exact geometric distance between them. The network processes this encoded geometry to classify whether the physical relationships between the duct, the artery, and the gallbladder definitively meet the criteria before the surgeon makes a cut. By processing semantic geometry rather than raw pixels, graph neural networks effectively mimic and verify the internal cognitive checklist of a master surgeon. All of this predictive power is useless if the system causes visual lag on the surgeon's monitor. The entire process, capturing the frame, segmenting the anatomy, calculating the geometry, and displaying the validation, must occur in under 100 milliseconds. Due to strict hospital firewalls and latency inherent in internet transmission, cloud computing is not viable. Every model must run entirely on local edge hardware, physically located inside the operating room. To execute this, developers rely on aggressive hardware optimization strategies, using software like TensorRT for mixed precision inference, which reduces computational load without destroying model accuracy. Engineers must balance strategic input downsampling and heavy model compression just to force massive transformer models onto edge GPUs. The evolution of surgical data science hinges on compressing immense logical capabilities into the physical constraints of the operating theater to objectively safeguard patient life.